Now we will present the design of synchronous sequential circuits using JK. We start with the JK flip-flops. But before that, we would like to make one note, which is when we used D-type flip-flops, the input equations are obtained directly from the next state equations because Q at time t plus 1 is equal to D of Q. However, this is not the case for the JK and the T flip-flops. In order to determine the input equations for the JK and T flip-flops, it is necessary to derive a functional relationship between the state table and the input equations. We know from before that for JK flip-flops, the output Q at time t plus 1 as a function of the inputs J and K, and the present state Q is equal to JQ prime plus K prime Q. And for the T flip-flop, Q at time t plus 1 equals TQ prime plus T prime Q. Now, having stated this, we would like to find now a relation between the values of J and K as related to Q at time t plus 1 and Q at time t. We write down the following table, which we call it flip-flop excitation table. For the JK flip-flops, we write down on the left-hand side a Q of t and then a Q of t plus 1, and we say if a Q of t was 0 and the Q of time of t plus 1 remains 0, what is the value of J and K? We find from the above equation that J must be 0 and K don't care. Why? Because if J is 1, a Q at time t plus 1 must be 1. Therefore, J must be 0. Now for K, if K is 0, it means no change. If K is 1, it means reset. And in both cases, a Q of t plus 1 is equal to 0. Now, when a Q of t is equal to 0 and the Q of t plus 1 is equal to 1, it means we have made a set state. And for this to happen, J must be 1 and K don't care. Because if J is 1 and K is 0, it means set. And if J is 1 and K is 1, it means toggle or complement. Therefore, from 0, we go to 1. Same thing exactly, or same logic. If Q of t was 1 and the Q of time t plus 1 is 0, K must be 1 and J don't care. And finally, if Q of t and the Q of t plus 1 are both 1s, K must remain 0 and J don't care. That is for the JK flip-flop. Now for the T flip-flop, it's simpler actually, because if a Q of t and the Q of t plus 1 are the same, whether they were 0, 0 or 1, 1, T must be 0. And if they are complement to each other, so if it was 0 and became 1, or 1 and became 0, T must be to make design using JK flip-flops. And for this, we assume that we are given the state table as we can see here. We have the present state and the input on one hand and next state on the other hand. And from these, we must derive the flip-flop inputs in order to be able to design the circuits. Now, looking at the next state, A at time t plus 1, it takes these values, 0, 0, 1, 0, etc. Same thing for B at time t plus 1. What we do, we will derive first J of A and K of A for using the present state A and the next state A exactly as we have done before. As an example, if A was 0 in the first two instances and remains 0, from the previous table, we see that J must be 0 and K don't care. So we write J is 0 and K don't care. And next, if A was 0 and it became 1, here 0 became 1, JK are 1x. So we write 1 and x here. And so on we continue. 0, 0, we have done it here, 0x. And then we have 3 times 1 and remained 1. And here, if it is 1 and remained 1, J must be x and K 0. So we write x and 0, and finally, when a is 1 and becomes 0, from the above table, we see that j must be x and k must be 1. We do the same thing exactly for j of b and k of b using the present state b and next state b, and we will not really do this. You can do it at your own time. You will find the results that we see in this table. Now, having obtained JA, KA, JB, and KB, we would like to determine next the equations for JA as a function of present state A and B and X, and same thing for KA and JB and KB, and for this we can make use of the Carnot map. So therefore, we take the values here for which are 0, 0, 1, 0, x, 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 x for JA as an example, and we put it in a Carnot map, and we do exactly the same for variables. We find that JA equals BX prime from here, and KA equals BX from here, and JB equals X, it is this loop here, and KB equals two loops, this loop and this loop, which we find A exclusive or X prime. Actually, once we have done this, we are set completely, because all we have to do is to draw two flip-flops, which are this flip-flop here and this flip-flop here, and this is A and this is B here, and this is A prime and B prime, and there is an input clock to both of them, and then we find out the external logic that need to be connected to the inputs of the flip-flops JA using this equation, and KA using this equation, and JB using this equation, and finally KB using this equation. And we see that we need two AND gates here for JA and KA respectively, and we need one exclusive NOR gate to KB, and JB needs only X, nothing more needs to be done. And this completes the design for the JK flip-flops. You need to exercise more on this. Now we take another example on the design using T flip-flops in this case, and the design problem that we take, it is called design a binary counter. Again, this is all that we are given. A counter is a circuit which counts 0, 1, 2, 3, etc. And if we would like to design a 3-bit counter, we first draw the state diagram, which are, we start with the state 0, 0, 0, and then at the next clock pulse, we go to state 0, 0, 1, and then 0, 1, 0, and then 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and from 1, 1, 1, we go back to 0, 0, 0, and so forth. This is the state diagram of a 3-bit binary counter, and draw the state table which we will need in order to complete our design. Now the state table again is so straightforward, because we write the present state on the left hand side, next state on the right hand side. Present state is A2, A1, A0, same thing for A2, A1, A0 at time t plus 1, and we say for present state 0, 0, 0, next state will be 0, 0, 1. If we are in 0, 0, 1, we go to 0, 1, 0, and 0, 1, 0, we go to 0, 1, 1, 0, 1, 1 to go to 1, 0, 0, which is 4, and from 4 we go to 5, 5 we go to 6, 6 we go to 7, and 7 we go back to 0, 0, 0. And having done this, actually now we need to find the flip-flop inputs. So we have 3 flip-flops. If we call them A2, A1, and A0, we need to find T of A2, T of A1, and T of A0. Finding T of A2, we look at the present state A2 and next state A2. And we use this table that we have just seen previously. Again, if A2 is 0 and remains 0, TA2 must be 0. And if A2 is 0 and it becomes 1, T must be 1. And if it is 1, remains 1, T must be 0. and if it is 1, becomes 0, t must be 1. So this is for TA2. Same thing exactly for TA1. We look at the current A1 and the next A1, and we note that it goes from 0 to 0, the first row, so this is 0. Then it goes from 0 to 1, which means it is 1. Then it goes from 1 to 1, which means 0. And then 1 to 0, which means it should be 1. And then 0 to 0, so it stays 0. 0 to 1, it has to be 1. 1 to 1, it has to be 0. And 1 to 0, it has to be 1. And finally, TA0, we look at present A0 and next A0. And here we see that A0 goes from 0 to 1, 1 to 0, 0 to 1, 1 to 0, and so forth. Therefore, TA0 will always be 1. And from these values, for TA2, TA1, TA0, we can again draw the Karnaugh, and we find the Karnaugh map for TA2. Here we have 2 1s. Therefore, TA2 equals A1 and A0. And TA1 has 4 1s here, which means TA1 equals A0. And TA0, as we noticed, it has 8 1s, which means it is always equal to 1. With this, now the design is straightforward, because all we have to do is to draw 3 flip-flops. This is the first one with input T, and the second one with input T, and that's the third one with input T. And there is one common clock that's connected to all the flip-flops, as we can see here. Now, starting with TA0, TA0 is equal to 1, so we put 1 here. And then TA1 is equal to A0, so we bring A0 here, and this will be the input to this flip-flop. And TA2 equals A1 dot A0, so we bring A0 here and A1 here to an AND gate, and we say this is T of A2. Well, if you would like to continue, actually, if we have one more flip-flop, by the way, we can, of course, draw the state diagram and the state table and so on. But I believe now you can guess if we want to have a 4-bit counter by adding one flip-flop called A3. We connect the clock pulse to the clock pulse, and T here will be equal to, we need one simple AND gate where we put this input here and this input here and this here, because TA3 will be equal to A2 dot A1 dot A0, and you are welcome to verify this at home if you want.